Hey, Honors Physics, this is Mr. Hausman. This is the beginning of the electric fields unit. Electric fields follow static electricity, and they are a perfect bridge to circuits. So most of us have never heard of an electric field in our life, but yet you've actually experienced numerous fields. We're going to use metaphors, we're going to use comparisons to existing fields to find out that you actually do understand some fields. So this little video that is going to play after this, right here on the right, is what you would have walked into class to see. On the left, you see a plasma sphere, you see some fluorescent tubes, and I know I did not record it flawlessly. Number one, I took my head out of the picture because I wanted you to mostly be able to see in low light the thing called the plasma sphere on your left. You've probably seen it in like a toy store or maybe in some kind of science novelty shop. This one's a pretty large one. It's about an 8-inch diameter. So take a look at that video and then let's jump to the next slide. We're going to be using metaphors to describe how something like a campfire or a backyard fire pit is a great example or a metaphor for thinking about electric fields. Why is that true? Well, like a electric field, all fields have sources. So here's an example of an electric field that might resemble something that you maybe have seen. Now, it's not directly the same. So this is a plasma globe. It's often used as a kind of a novelty, just kind of like a sciencey piece of equipment. But what it really is at the center of that sphere, there is a cathode tip that's generating charges. And it's surrounded by argon gas. Argon gas glows in that pink-purple range, depending on how it's being excited. And what it's being excited by is the high energy charges that are the source. That pink thing in the middle is creating very high voltage. So this is actually technically more dangerous than a Van der Graaf generator, but we're also protected by the fact that we have this gas around it and then we have this glass sphere. So no one would ever want to touch that. So what you notice is that toward the center, it is the strongest. It is quite intense at the middle, and the field surrounds it in all directions. In fact, a lot of people may not know this, but in order to get a fluorescent light bulb to glow, all you need is an electric field. That electric field causes the charges in the fluorescent tube to move or to be excited. And notice there's no wires hooked up to this end of the fluorescent tube. And it goes all the way down to wherever my hand is. So if I move my hand, and it's because I'm having an effect on the electric field. So it radiates outward in all directions. That'll be something that we look at in our introduction to fields. This small fluorescent tube is essentially the same thing. It's just multicolored. And notice that when I bring my hand near this tube or near this tube, it seems to have an effect. My body is changing the shape of the electric field because even though I'm not charged, I am directing that electric field toward me. And it creates that kind of attraction. A lot of people think it's just like super cool. And if you put two or your whole hand, but essentially what we're doing is we're visualizing an electric field around a plasma sphere. Here's one last example, a light bulb lighting up with absolutely any electricity flowing through it. And you might think, why aren't we just doing this in our homes? Why don't we have wireless electricity everywhere? And the answer is that. The electric field gets weaker with distance. So all of your light sources, all of your electronics that would want to be powered by an electric field would have to be relatively close to the source, or you'd have to have a stronger source. So kind of a fun demonstration to start off the electric field unit. So here's page 2. Page 2 is an introduction to these metaphors where we're going to write down some of the main ideas in case the video wasn't perfectly clear. So there's a lot of science fiction around shields or fields. A superhero puts up a shield or for himself, herself, a village, a community, a spacecraft. And shields are actually based on the physics concept of a field. They're real quantities, they are vector quantities, and we're going to use them to understand where forces come from. So a field is nothing more, right, than a physical quantity that has a magnitude and direction. Oh, as soon as you see that, right, that means these are vectors. Fields are vectors. And it depends on the object's position near a source for that field. So like a spacecraft might create its own field, and then depending on how close or far away from that is, that might change how you experience that field, okay? So let's do a really simple analogy. So here's a fire pit in your backyard, okay? Maybe a campfire. And if you stand close to the fire, you experience it very differently than if you're 3 feet away, right? You get a different amount of heat. It's more comfortable standing a few feet away. And then if you're very far away, you might experience it totally differently still. Maybe it's too weak a fire to actually feel any warmth, and you get kind of cold back there. So we know that a fire pit is a way to do a comparison to a physics principle called fields. So all vector fields, right, have vector characteristics. That means they have different magnitudes and they have different directions, and we'll examine that. The first thing that we should examine is what's the magnitude of a field? Well, it depends on the position or how far away you are from the source, right? There will be a different magnitude or strength for that field depending on how far away you are. So if you have ever been to a backyard fire pit and gotten too close, it kind of feels like your feet are getting hot or maybe your shins are getting too warm, and that's not a comfortable spot. Again, 2 or 3 feet away, sitting on the couch or the chair, this is sometimes the perfect spot. And sometimes they make this funny kind of analogy that it's sometimes called the Goldilocks location. They actually use it for planets relative to stars. If you're too far from a star, there's not enough energy to sustain life. If you're too close, it's too hot for chemical reactions to happen. So, like we have different magnitudes depending on how far away we are, right? Too hot, too cold, or just right. So each of these rings has the same strength, right? Are you on the black ring that's right by the fire pit? Well, then that's all super hot. Then just the right distance away, or this weaker outer ring. So notice the magnitude of the vector really depends on how far away you are from the source. So what's the source in each of these cases? Well, for a fire pit, it's the fire, right? So all vector fields have a source. But for our analogy, right, the source of the field is whatever you're burning. Are you using a wood fire, or are you maybe using propane? That depends on, if your family wants it to be smoky and have that authentic wood smell, or propane just gives you the warmth without all of the other stuff, right? Everyone's got a different aesthetic. So a fire pit is a metaphor for a vector field. So let's go now look at a vector field that you actually do know about. You've known about it probably most of your life, and that's a gravitational field, okay? So we're going to start with one. We're going to examine gravitational fields. Then we're going to learn about electric fields in this chapter. And then the third kind of field we're going to learn about are magnetic fields, but that's not for a few chapters ahead. Let's spell that right, magnetic fields. And are there others? Well, electric fields, magnetic fields, gravitational fields, they've been known for hundreds of years. The electrical and magnetic fields more like 150 years, but they are still discovering new fields. In fact, 12 years ago, in 2012, from when this video is recorded, they discovered at the CERN collider in Switzerland and France, at the CERN collider, they discovered something called the Higgs field, created by a Higgs particle called a boson. And the Higgs field is the newest, it's really quite young, created at CERN or discovered at CERN by particle collisions. And we think that the Higgs field is actually what gives every object in the universe its mass. And that's an oversimplification of exactly what's going on there. But the Higgs field and the Higgs particle was introduced or suggested that it might exist in the 1960s, and it took until 2012 to actually confirm it. So fields are very common in physics. You just haven't seen them yet. So let's go to a gravitational field that you actually have heard of. So, right, everywhere you put an object, there is going to be a vector field. In this case, we call it a gravity field. The symbol for that is a G. What is G? Well, it's the same G we looked at this fall, and it's the rate of gravity. So if you were to put an object anywhere on the surface of the Earth, right, along basically the surface of the Earth, you would say that at all points, the gravitational field is G is 9.8. Now this fall, we used the units of meters per second squared. And that's correct. That is the acceleration due to gravity. But wait a minute. I think what you just heard, though, is that in the fall we mentioned gravity as an acceleration, but in reality, that G can change depending on where you are. Are you on the Earth's surface? Are you 10 miles up? Are you 50 miles up? Are you 100 miles away from the Earth in our atmosphere, or even outside of our atmosphere? So the rate of gravity is kind of a measure of where you are relative to the Earth, okay? So let's examine what causes gravity, right? Because everything has a source. Every field comes from a source. Well, it has a mass. The mass of our planet is what we believe creates the gravitational field. Now, fields are vectors, so they have a direction to them. And gravity has a direction to it that's always inward. Notice all of these arrows point toward the center of the Earth. It's always an attraction. Okay, so it's one direction only. So for every single mass, whether it's a planet, a star, a black hole, the gravity, right, field would be toward the mass. So those are little vectors, and we'll draw them better in later units. So what we're saying today is that while the G field changes depending on distance, we do know it at one place, and we will actually still use the same letter, but now we're going to change its units. The units for the field, the gravitational field, are newtons per kilogram, right? These are the units for that. And you're like, but wait a minute, those are different than over here. They're actually not. That's the same unit if you simplify a newton divided by a kilogram. So when I was becoming a physics teacher, I kind of had to make the realization that in some ways an acceleration, which you kind of understand, a change in velocity, it's an influence that makes things change their position and their velocity. Well, that's exactly what a field is, right? They are creating, right? These fields are creating a force. So gravity, you understand, it has mass as a source. It's always an attraction. Let's try something new. Let's go to an electric field. So when we looked at the plasma sphere, the demo piece of equipment, we saw that it radiated outward. But what I forget if I mentioned in the video, but what is the source? In the center of that plasma sphere, there was a little bit of a pink little kind of top, right? And that was the source of the E field. And so what was that? It was a bunch of charges. In fact, it was very highly charged, right? So here's an example, right? The source of the E field were the charge or charges in the center. Now, you could see these little tendrils, these little like things radiating outward, and that was actually showing you the direction and the shape of the field. But electric fields are a little bit more complicated than gravity. So the direction of the field can change. It depends on the sign of the source. This was not in the video that I showed you, but essentially positive sources, right? Well, their fields go outward. The electric field from a positive source goes, I said outward and wrote outside. Let's clean that up. It's outward or away. A negative charge, on the other hand, has an E field that points inward. Okay? E fields change their direction depending on what the sign of the source is. Now, we couldn't see the shape or the direction. All we could see was that it went out in all directions. So the symbol for an E field is a capital E. That makes sense. E field, capital E. But the unit is not the same as gravity. Now, the unit is newtons per coulomb. And you're thinking, wait a minute, there's one field up here that has newtons per kilogram. Now the unit is newtons per coulomb. So this is weird. Fields do not have all the same unit. What they have in common is that there will always be a force on the top. And then the unit on the bottom will be what is the unit of the source, right? The unit of the source. So it's force per coulomb, newtons per coulomb for an electric field, but yet it's newtons per kilogram for a gravity field, because masses are the source. So that's actually pretty easy to understand, but fields are a little bit different, okay? So here's a question I'd like you to try, which is, which one of these positions, A, B, C, D, E, or F, is the strongest? Let's go from greatest to strongest. And the strongest field would be B, but you notice very quickly that C has the same strength field. Then you go a little further out and you notice that A and D have the same strength field. They're second. And that gets us to letter F and to letter E as the weakest position. And how did we know that? It's because it's the farthest, the weakest, because it is far from the source. Think about a fire pit, right? It's always weakest the farther are you away. Okay, this page is perhaps the most challenging. So forces on charges in E fields. Okay, so in fact, we're going to start with this, right? What is the purpose of a field? Well, or kind of what's the driving principle? Fields, having a little trouble writing close to the edge of the screen. Fields create forces. Now, there's many kinds of fields, so that's why there's many kinds of forces. So let's start on electric fields. An electric field surrounds a source, right, has a specific shape, and it has a certain strength, magnitude. So that means really it has a specific vector property to it. So the charge source, so everywhere in the middle, there's a charge source, and it alters the space around that charge so that another charged object will experience a force. So you have a source, and then you put something into that field, and it gets pushed around. So for electric fields, you have a source that's maybe a positive Q, and you put in another charge. Well, let's put in an electron, or maybe let's put in a proton. And here's the source in the middle, doesn't matter its size, and you know that an electron and proton would get pushed or pulled because it's near there. And the reason is because there's a field. So we know that charges can be attracted or repelling, but it really depends on the sign of the particle you put in the field. So for example, a proton would get, oops, that is not my best work. A proton would get pushed away because it would get repelled by a positive source. An electron, on the other hand, would get pushed or pulled inward. And that's different, right? So each particle has a different response to that field, okay? So let's go back to blue. An electric field is a region in which a force can be felt on a charged object. So that's the specific responsibility of an electric field. An electric field is an invisible space around a charge that can create a push or a pull on any other charged object. So let's do a quick comparison. So we have a source charge, okay? It's like a table. And we've already heard that the way that you draw this is that for a source charge that's positive, the electric field points outward. Okay, let's just do 4 lines, but let's label that. That's not a force, that's a field. It's invisible. And then you put a test charge in there. And the answer is, what kind of test charge? Well, let's test it with a positive. So let's put a positive near there. Well, you know that a positive is repelled by a positive. Pretty obvious statement. So it gets pushed away. If we dropped an electron in this field, not shown in the picture, I just added it on the other side, well, that would go towards the positive source, okay? So what way is the force? Well, that's not a new skill. You just ask, what do positives do to positives? They push away. Electrons are attracted towards it. So now what I want you to do is I want you to compare the direction of the force to the direction of the E field. And that's an important thing to consider. So here's the E field. And we said a minute ago that the force was out, right? The force was away from the charge. So do you notice that the force and the E field are always in the same direction? The direction is always the same. but only for a positive test charge. An electron always goes against the E field. Want me to prove that? Well, you said a minute ago that this electron is attracted to the positive, but yet the E field is outward. So the electron is pulled in, but yet the E field is out. And you might say, but that's confusing. Why doesn't it go with the E field? So the general principle that we're going to summarize is that no matter what the source is and what the charge is that positive test charges always go in the same direction, right? They go with the E field. Negative test charges, on the other hand, or any negative that you put into an E field, always go against or opposite. And my students have found that it's much easier to sort of memorize or maybe kind of take to heart that positives in E fields go with. That means they go the same direction. Electrons in E fields go against. And it's a pretty simple principle. And you say, well, let's prove it. Let's see, does it work the same when the source is negative, right? So now let's change to a positive source. And the answer is, okay, we put a positive there, and it would go towards. And a negative would go away because they are repelled. And now what would be the shape of the E field? Well, E fields around negatives are inward. This is the E field, not the force, the E field. And the electric field would be the same direction as the direction a positive would move. Yeah, it kind of works out the same for both pictures. Okay? So let's finish with the bottom of the page, okay? Let's talk about how to draw these field lines, because I didn't show you how to do that yet. I just asked you to take it for granted that the E field lines go out of positives, go in toward negative. So let's finish with this, okay? Field lines show the direction of force that a tiny positive would experience. So if someone says, which way do they go? Well, they go out of a positive source and they go in toward a negative. You can either memorize it or you can use logic to kind of remember how it works. They go away from positives and in toward negatives. The line density, how close the lines are, shows, right, it's about the closeness together they are, means the strength, right? So the closer together, the stronger the field. We'll do some drawings of this. Let's keep going. E fields never cross. So down the road, you're going to see more complex charges, not just point charges. See how this is just a positive point and this is a negative point? Well, eventually we're going to have other shapes. But one of the principles is that electric fields never cross. They curve due to superposition or vector addition. Okay. The last bullet is one that we're going to see when we draw these in more detail. They are always drawn perpendicular to the charged object's surface. Okay? So field lines come out of positives, they go in toward negative. The denser they are, the stronger the field is. They never cross, and they're always perpendicular from the surface. So let's finish with this. This is an example of superposition or vector addition. So this is the first complex system we've done. Let's zoom in on this. This is a positive and a negative that are neighbors. They're not connected, but they're in the same space. And we know that the electric field for a negative charge is inward and it's outward for a positive charge. So what is point P? Well, this is just a place. It's some place that you're interested in the field. So let's use some black lines. So a minute ago we said that E fields go in toward negatives, but we're going to go through point P. And we're going to try to make it as straight as we can. Then if we draw the electric field for the positive Q at point P, it would come outward. I'm going to make it be a dashed line. Whoops, I just missed the dot by a tiny bit. So now what we're going to do is we're going to break those into components. So let's call this, right, this is E field blue, and this is E field red. So the blue one is, oops, let's go blue. The blue one has, if someone said do the component, it would have a negative x, and it would have a negative y. We're not worried about the exact angles or calculating them. We're just trying to show that if you're in the third quadrant, like this E field is, you'd have a negative x and a negative y. The red E field would have a negative x, but it would have a positive y. Negative x, positive y. And I hope you notice that the y's are basically canceling each other out. You might not say they're the right size, but they are opposite direction to each other. And so they actually create a net field that is entirely horizontal. The E field at point P would be the sum of those two vectors. And so if someone said, what's the E field at point P? It's not actually out, away, or inward. It's actually kind of this parallel line. And it shows you that that field is really complex and you have to do vector addition. So if someone said find the E field here and here and here and here and down here and here, you'd have to do a lot of vector addition. And you can do this with software very easily and what are called matrices, or a matrix in math, okay? So that's a great place to finish. We're going to do a little bit more with these on the next lesson.